In this video you will learn what the term voltage actually means. You will learn how it can be derived based on the definition of the electric field and also on a distance over which charges move in a circuit and on which electric work is performed in the process. If you want to dig deeper, this is a very superficial video here, then also take a look at the next video on the actual derivation of the electric voltage from a number of base parameters. My name is Andreas from The Fearless Engineer, and here we go. Now let's start with a broad definition of the term voltage. And if you take this excerpt here from a German dictionary, we can say that voltage is described as the difference of the electric potentials between 2 points. And due to this difference, current can flow between these 2 points. So voltage is the driving force behind the movement of charges in space or in a circuit, in a conductor. That's the important takeaway from this definition here. Let's further continue with a short review of what we have learned already in previous videos. We have seen that the electric current I is defined as the amount of charge in a given time t that passes a counting station, which might be a multimeter which measures the amount of charges passing by. And it's described by this very simple relationship here. The current I is the ratio of charges and time t. And the reason for the movement of the charges is the electric field E, and this field has a certain strength and it has a direction in space, and this field causes a force F which is applied to the charges moving along, and it's pushing the charges and it's pulling the charges at the same time. And the charges move against, as we have seen before, against the direction of the field. And now we want to look at a very interesting analogy between charges in a field and gravitational force pulling apples from a tree down to the ground. On the left hand side here you can see electric charges, which are the blue circles, moving against the direction of a field E, and this field is caused by the terminals of the battery here, positive terminal at the bottom, negative terminal on the right. Inside the negative terminal there's a surplus of electrons, inside the positive terminal there's a shortage of electrons, and this field propagates through a conductor, and inside the conductor the field causes a Coulomb force to push away charges from the positive and pull charges towards the negative terminal. So the field E is the cause for moving electrons. And in the Earth's gravitational field we have an apple, and this apple is pulled towards the bottom by the gravitational field G, the G force, and this is a very, very easy to understand and also to compare example to the left here, where we look at the motion of electrons in a field. The only difference here is that the apples are moving into the direction of the field and the electrons in the example on the left are moving against the direction of the field. And on the next slide we will see that the formula with which we describe the motion of electrons is very, very similar to the formula describing the falling motion of apples. But before we get to these equations, let's first talk about electrical work and also voltage. Now when an electron, or apple in the example we have seen, travels a certain distance in the field in which it is pulled towards or pushed away from some source, work is performed on this electron or apple. And the greater the field strength and the greater the path length over which the mass travels, the more work is performed on it. So if we imagine an apple hanging in a height of 2 meters in a tree and it's falling down, a certain amount of work is performed on the apple during its falling motion over this distance of 2 meters. And you can easily imagine that if we look at another apple hanging in 4 meters, so double the height, more work is performed on this apple when it falls, and the distance to the ground over which it's going to fall is 4 meters. And the electric voltage U, which we want to define now, is simply the product of the field strength E and the path length L between 2 points in space, and it describes the ability of the field to move charges from one point to another. So imagine these two point charges here, one at the bottom, one at the top, and in between these two charges there is a length L, and the voltage simply describes the potential energy that is lost when we move this charge here from the bottom, which is very close to the positive terminal, which corresponds to the apple hanging in 2 meters, to another height, which might be this position here, which is only, let's say, 1 meters above ground. And depending on the length, the apple or the electron loses a certain portion of its potential energy. And the loss of potential energy is exactly what is described by the electric voltage. And this is why we have this very simple formula here. The electric voltage is simply the product of length multiplied with the electric field. And we measure it in the unit volts, which is abbreviated by the letter V. The problem is, or not the problem, but what you have to keep in mind is that even though we can describe a loss of energy by using the concept of voltage, the voltage says nothing about how many charges are moved. In the example, we have only considered a single charge, but obviously this relationship also holds for 10 billion charges. So the concept of voltage does not take into account the amount of charge that's losing potential energy. It only shows us, based on the length over which electrons move and on the strength of the electric field, how much energy is lost for each individual charge. And the information about the amount of charges, this is contained in the electric current I. Now, this was a very brief definition of the electric voltage, a very broad overview and a very quick walkthrough through this idea of losing kinetic energy by moving through a field, and also this analogy between the gravitational field of the Earth and the electric field of a battery, for example, or another voltage source. This analogy between these two fields, gravitational field and electric field, is something which we elaborate deeper on in the next video, which derives the concept of electric voltage from a number of base equations, and which also relates these two equations, the energy in the gravitational field of the Earth and the energy in the electric field of a power source, to each other, and shows how we can arrive at this final definition of electric voltage based on the loss of energy. So if you are interested in knowing a bit more, watch the upcoming video on this formal derivation of the voltage. And if you like this video here, please leave me a thumbs up and also maybe subscribe to my channel. And in case you have any questions left, don't hesitate to drop me a comment in the comment section down below, as always. And I wish you a nice day now. See you next time here on The Fearless Engineer.